Hello, I'm Vibha, and we're going to look at some of the applications that we use NAME for. So our team in the Met Office is called ADAQ, the Atmospheric Dispersion and Air Quality Team. And as a group, these are kind of our main responsibilities. Emergency response, we work very closely with a team called EMARC, and they sit in the operations center in the Met Office, which is the 24/7 part of the office. In the case of an event, for example, some kind of chemical incident or a volcanic eruption, EMARC will be the first people to respond, and part of that response will be issuing a NAME forecast. We work with planning, so for example, nuclear sites. We will look at something called a what-if scenario. So if there was some kind of incident, knowing what is kept at that site, what could happen. In a similar vein, we take part in various exercises, and that's for all sorts of applications. For example, animal diseases like foot and mouth disease. So we'll run through the process of running NAME and producing forecast output and passing that on to the other agencies and decision makers that would be getting that in an actual event so that they can run through the exercise of interpreting that information and making their decisions. We'll also look at post-event analysis. So during an event, we'll have a limited amount of time. We'll also have a limited amount of information, especially about the source. So after the event, we might go back and run more detailed NAME runs and perhaps with more accurate information about the source and potentially be able to compare these to observations to see how the model is doing and how we might improve those initial runs in the future. As the name suggests, we have an air quality part of the team as well. At the moment, our air quality forecasts are produced by a model called AQUM, which is air quality within our numerical weather prediction model, the UM. But now we're also looking into using NAME for air quality forecasts. And finally, research. So this can be very wide-ranging, and some of it would underpin all of the applications. For example, if we're researching some of the things that were mentioned in the core science talk, and other things might be a bit more specific to particular applications. For example, looking at the behavior of volcanic ash particles and how they might fall through the atmosphere. So first of all, we'll look at chemical dispersion. In the case of a chemical incident, the first people in the office to respond would be EMARC, who work in the operations center 24/7, and they will issue something called a CHEMET. So the CHEMET service needs to be fast, the output needs to be sent from the building within 20 minutes, and it's looking at short-range predictions. The forecasters on the EMARC bench will also provide instant telephone advice. And this CHEMET service is available to all Cat 1 and Cat 2 responders, so Blue Lights, Public Health England, Environment Agency, etc. In a CHEMET run, there's a single NAME run, and from that run, several different plots are produced. One of them is this top run here, which is an area at risk map, and it's showing relative concentrations. And this is because during an event, we often have very little information, or perhaps even no information, about the source strength, which is why these are useful. But it does also produce some plots like this, showing air concentration or deposition, which can be especially helpful if we do have information about the source strength. So back in 2005, there was this accident at Buncefield, which caused a very large fire. And on Sunday here, there were very light winds and stable conditions. And the CHEMET was produced by a model called ADMS, and it used just 10-meter wind fields. And because it was stable conditions with light winds, there was a lot of wind shear, which then wasn't picked up by the model. So in the CHEMET run, you can see that the plume is going kind of eastwards and southwards, whereas when you look at the satellite imagery, there's actually a lot more going towards the west. And this kind of demonstrated the need for having 3D met fields available for these kinds of runs. And you can also see the difference between stable conditions with light winds where the plume is quite spread out, and conditions with stronger winds where there's a very thin, narrow plume. So now we'll look at radiological dispersion. In the case of a nuclear incident, the Met Office will primarily be looking at the impact on the UK and any UK citizens abroad. Here, there's a video of a name simulation for the Chernobyl disaster, and the bright colours are showing the heights of the particles, and the various grayscale colours are showing the concentrations of cesium-137 that have been deposited on the ground. In this incident, the plume took about 5 days to reach the UK, and then the impacts were largely due to the rainfall and there being a lot of deposited material. So we'll look at plume prediction, but also we can run name backwards to help with source identification if some radiological material is detected and the source is unknown. And name will simulate the radioactive decay of the species, both when it's airborne and after it's been deposited. We have an international commitment to have this forecasting capability available, and we take part in regular exercises. Initially, during the Fukushima accident, name runs were carried out at the Met Office, but the way this happened was that ONR had source information that was sent to us, and we used that to do our name runs. And then the output data from our name runs was emailed to HPA so that they could do some dose modeling to look at the health impacts. And this was all very clunky, having to email data to each other. So the JAM modeling tool was invented, which is joint agency modeling. So first of all of the source data that's predefined by ONR is in a database for us to use. And this is based on all the nuclear sites and what is known to be there. This information will be used initially, but during an incident, as we might find out more about how much is being released, this can be modified. And this source information, together with the weather forecast, will be fed into NAME to produce a dispersion forecast. And then this output will be sent into some dose modeling code that's owned by Public Health England. And this code also will run on Met Office computers so that it's all run in the same place. And then from that, some graphical output will be produced, and this will be looking at all sorts of different things. It produces a nice PDF with sorts of various potential releases and various situations and various types of dosage that you might be interested in, and this is sent to all the people that need it to deal with the situation. NAME is also used for plume predictions of volcanic ash and volcanic gases. So the Met Office is the home of the London VAC. A VAC is a Volcanic Ash Advisory Centre, and they give predictions of where volcanic ash is going to go for the CAA, the Civil Aviation Authority, as well as airlines and airports, to help them decide where it will be safe to fly in the case of a volcanic eruption. There are 9 VACs around the world, and each has an area of responsibility. The London VAC is here and has this area that includes the UK and Iceland. So even though it's a fairly small area, it does include all the very active volcanoes in Iceland, as well as some of the busiest airspace in the world. One of the most notable events that the London VAC has been involved with was the Ayo eruption back in 2010. And many of you will remember this. It caused a lot of disruption in aviation. Flights were grounded for a long time. It was a very big volcanic eruption with a lot of ash, and also it lasted a very long time. As well as volcanic ash, we can predict volcanic gases. This isn't part of what is necessary from a VAC, but if there was a very gaseous volcanic eruption, it's something that we would probably be asked to do. So in this top plot, it shows the satellite imagery of some SO2 that's been released. And in the middle plot is the name prediction for SO2. And name can also include the chemistry for secondary sulfates to be predicted. And here is the plot for that. We also have an inversion modeling scheme called INTEM for volcanic ash. So in a volcanic eruption especially, it's very difficult to have the correct information about the source term and how much is being released into the atmosphere. You can try to look at plume height, but even estimates of the plume height may not be very accurate, as well as if, for example, it's windy, the plume might be curved over and may not look like as much as being released as it is. And it also changes over time. So what INTEM does is that it starts with an a priori name run. So this is the sort of initial run based on what we think the source might be. And it also takes in some satellite observations. And it takes the name run output and the satellite observations from the same time. And the satellite observations in some places can give us some column loading, and in some other places, shown by these green spot spaces, it can show us where there's clear skies. And using that information, INTEM will produce a new source term, and this source term will change in height and change over time, so that when you run with this new source term, you get something that looks a bit more like what you're actually seeing, and then you can continue to run forward from there and hopefully get more accurate results from those runs. Predicting the spread of some animal and plant diseases can also be aided by name plume predictions. An example of this is blue tongue, which is a disease that primarily affects cows, and it's carried by midges. So a midge will bite an infected animal, and then when it goes on to bite further animals, it will pass the infection on. Blue tongue first arrived in the UK in 2007, and other strains continue to spread around Europe. So during blue tongue season, which is around April to November, name runs are done twice daily at around sunrise and sunset, because that's when midges are most active. Midges are very small, and so their long range travel is determined essentially by the weather and the wind speed and direction. So in these name runs, it will take the sunrise and sunset times from the numerical weather prediction model, as well as the meteorology, and take into account things like precipitation, because if there is heavy rain, then the midges are less likely to take off. And once a fortnight, a report is produced about if there is an outbreak along the coast of Europe, where in the UK might be affected, so that people can plan for that if anything came up. And lots of other animal and plant diseases as well. So for example, this here shows a picture of wheat rust, which is a fungus affecting the wheat crop, and it can affect yield by a significant amount. And the spores of this fungus are spread by the wind. So in terms of model development, one of the things that the team is looking at is the use of ensemble forecasts. So I've mentioned things about uncertainty, especially around the source terms, but there are many places that uncertainty comes into play when it comes to a dispersion forecast. So we have the uncertainty in the model, in the source term in the model, as well as the dispersion model itself and the parameterizations involved in there. And we obviously have the NWP data going in as well, has its own uncertainties. So by the time we come out with our plume prediction, there are uncertainties around the spatial position of the plume, the timings, as well as things like the deposition. So for example, if there's uncertainty around the precipitation in the NWP fields, then when it comes to the plume prediction, if there's a lot more or a lot less precipitation and therefore more or less deposition, that can have an impact as well. So we're looking at being able to move towards using ensembles in our operational forecasts. Ensembles and probabilistic forecasts are becoming more and more widely used in weather forecasting, and in particular including being used downstream, for example in applications like flood forecasting. And as this happens, there's becoming an increased recognition both by dispersion modelers and users that the uncertainty in dispersion cases is important to know about and understand. Initially, we'll be focusing on the uncertainty in the meteorological forecast, although longer term we'd like to look at some of the other introductions of uncertainties as well. So here, this is an example of what we would call a postage stamp plot. So each little plot shows a potential weather forecast, essentially, and normally we would just take one of these to be the deterministic forecast and run our dispersion model on that. But the idea would be to run name on each of these possible weather prediction outcomes to see what kind of uncertainty there is due to the meteorological fields. And the hope is that we would eventually have real-time ensemble-based name predictions available to EMARC in the Operations Centre. And this would be alongside the products and services that they currently have. So it wouldn't replace anything that they have. It would just be in addition to provide extra information about the uncertainties around the prediction that we're giving. So one of the things we need to think about is how best to display these results. I showed the postage stamp plot earlier. We could have a similar thing with name plume predictions on a postage stamp plot, but that's a lot of information to look at, and especially in an incident, you don't want to be overwhelmed with too much information and too much to look at and interpret in a short amount of time. So one of the things we're considering is percentile plots for the location of the plume, or something like this, which would be the number of ensemble members that agree with a certain threshold being exceeded in the air concentrations. So there are many possible ways we could display these ensemble results to kind of try to help explain the uncertainties around our forecast. And this requires a lot of working closely with people in EMARC and also other users of our output to help give them the information that would be most helpful to them. So we also have post-event analysis and looking back on events that have already happened. We have a Met archive that allows us to run for historic events. So especially bigger events like the Aya eruption in 2010 and Fukushima and things, we can come back to those after the event when we have more information, especially I've mentioned a few times about the source term being very unknown at the time of the event. Afterwards, we might have more information about that. We also will have an improved model, improved weather data, and we'll also have observations to be able to compare to. So it's very helpful to be able to rerun for these old events and see how the model is doing and how it could be improved. And all of these require collaborations with many organizations, including a role for EMARC, our emergency responders in the Operations Centre as well. So these collaborations are extremely important, especially when it comes to applications. The applications are so wide-ranging and we are not experts in everything. We know about the dispersion component, but each application has its own nuances and we don't know about those things. So here is a picture that shows some of our collaborations, some of our partners, and yeah, we couldn't be doing all of the work that we're doing without these very important collaborations. So yeah, we've gone through some of the applications that we use name for. We talked a bit about volcanic eruptions and volcanic ash, the Volcanic Ash Advisory Centre, chemical accidents and the chemet plots that are produced from that. There's also forest fires, which we didn't talk about, but name can be used for that as well. And we looked at animal and plant diseases as well, carried by midges and things. There's also air quality and haze forecasting, plant diseases like wheat rust carried by fungal spores. There's also general emissions and aerosols and dust, for example, Saharan dust events, and nuclear accidents. And to be honest, the list goes on. There's a lot of applications that name can be used for, which means that there are lots of specific bits of name that are used for some applications and not others. So yeah, that's kind of a bit of an introduction to some of the applications that we use name for. And I'll see you in a bit for some questions and discussion.